more beneficial for you guys if you have specific questions that you want to ask, to maybe have you guys ask some questions, and that can help guide the discussion. If not, I've got some things that we can certainly talk about to help motivate maybe some questions. But are there any questions that people would like for me to address before I just start talking? Nobody? Okay.
Yeah, can you go over diamagnetic effects and how that pertains to...
I can certainly talk about that. Let me get the slides open up. I've got two different computers going, so let me open up the slides for the NMR stuff. It'll be okay. To talk about it in that respect. What I will say is there's not... Okay, here we go. Let me get my laptop up on those screens because that's the easiest way to talk about this. So this relates to the chemical shift that you would expect to observe for all the animations. But what's the primary factor that really affects chemical shift? Let me ask you guys that question. Right, so what's going to cause de-shielding primarily? Shielding is when there's a lot of electrons around the nuclei that you're probing. De-shielding is when something is causing there to be less electron density. So what's the most common cause of de-shielding? Electronegativity. So by far, if I go back and just jump back a couple more slides, we were looking at the
and I was just like, nah, fuck this one.
There we go, that's the slide. Primarily, what's causing chemical shifts to move downfield towards the left, remember downfield is to the left, upfield is to the right, is a nearby electronegative group. So if you have something like oxygen or nitrogen, right on the same carbon that's bearing a hydrogen, that's going to cause the signal for that proton to come into resonance at lower applied field strength. The electronegative group draws electron density away from that hydrogen, and that means you don't have to bring as high an applied field to get that to come into resonance. The local field that's generated by the nearby electrons will be a lot smaller when there aren't a lot of electrons nearby. So, we talked about the fact that sp2, sp hybridized carbons are more electronegative than sp3. As you increase the percent S character, you're making those hybrid orbitals more compact, you're bringing the electron density closer to the nucleus. If the electron density is closer to the nucleus has a stronger pull on that electron density. So the expectation would be sp hybridized should be even further downfield compared to vinylic or aromatic. But when a proton is directly bonded to an sp2 hybridized carbon, its signal is going to show up somewhere above 4.5. Aromatic region is 6.5 up to around 8. Why don't we see acetylenic protons directly attached to an sp hybridized carbon, even further downfield? Well, the other factor that comes into play when we're looking at chemical shift is when there are pi electrons. When you have pi electrons present in a molecule, and you put that molecule in an external field, a magnetic field, electrons in the presence of a magnetic field start to circulate. That's just the physics of the situation. Now, when you have a charged particle in a magnetic field, it induces movement of charge. Well, when we have pi electrons, this is the picture that we utilize for just a typical alkene. The pi bond in an alkene is basically sandwiching the atoms that are all on the same plane. This is just ethylene, but when you have sp2 hybridization, the carbons and each of the things that are singly bonded to them are all on the same plane. So you basically have a sandwich of pi electrons above and below that plane. Well, those pi electrons start to circulate in closed loops. And because of the physics, when you have that movement of electrons in closed loops, moving charge itself generates a magnetic field. Okay? Well, it's where you are with respect to that loop of circulating electrons that determines whether the local field is reinforcing the applied field. And it's just the physics outside the loop. That local field that's generated by the circulating pi electrons is in the same direction as the applied field. So that there it's reinforcing. So if the protons, and that's where they're going to be, if it's an alkene or an aromatic ring, if you've got protons outside that loop of circulating electrons, they're going to require a lower applied field to come into resonance. Lower applied field means they're de-shielded, the signal's downfield. Okay? It's when you have something inside that loop, inside the loop is where the local field opposes the applied field. That means you have to use a higher applied field strength. Well, that's what we've got when we have an alkyne. An alkyne doesn't just have one pi bond, it's got two pi bonds. So there's basically a cylinder of pi electrons encapsulating the carbon-carbon bond. Well, the way those pi electrons move, it's going to circulate in a loop, but the loop is now kind of around the carbon-carbon bond. Outside the loop, the local field reinforces the applied field. That's not where the protons are, though. Because of the linear geometry, a proton directly attached to an alkyne sp hybridized carbon is inside that loop of circulating pi electrons. Inside the loop, local field opposes the applied field. What does that mean? To get those protons to come into resonance, you've got to go to larger applied field strength. The signal shifts farther to the right, farther upfield. Basically, this cancels the electronegativity effect. We would expect to see sp hybridized protons on sp hybridized carbons all the way downfield, maybe around 10. Well, this magnetic effect basically cancels that electronegativity effect. So it's not all that different from where normal aliphatic protons show up. Does that answer the question to your satisfaction? So, again, you can get valuable information based on the chemical shift. Let me go back to those generic ranges. Somebody asked me this the other day. Now, I'm going to give you a whole bunch of specific chemical shift information. Where is that? General. There we are. I'm going to give you a whole bunch of specific chemical shift information. Last 3 pages of part 1 of the exam are going to have that detailed information that I posted in Canvas. The worst way to approach a problem where you're trying to determine a structure given spectroscopic information is to look at where chemical shifts are, try to match them up to what you see in that detailed table. Oh, there's something at 2.5. Well, let me look at the table. Oh, here's something 2.5. Doesn't necessarily mean you got that exact thing in your real molecule. That's really useful for confirmation. Once you use kind of the generic ranges, you think about kind of, the puzzle pieces and put them all together. Does it all fit with the data? That's really the best way to use it. So if you've practiced enough problems, you shouldn't even need to refer to that really specific information. It's really just there for confirmatory purposes. Hand up, question.
Yeah, so going back to the alkene, so if it's outside of the loop, it reinforces the applied force, and that de-shields the molecule.
Right, because if the local field is in the same direction as the applied field, you've already got a field pointing in that direction. So that means the applied field to bring those protons into resonance doesn't need to be as big, because you're getting some help from the pi electrons that are already in the molecule. Okay, so that's why when you've got pi electrons, you tend to see, again, for sp2, it's because of the geometry. It's the same thing for an aromatic ring. The protons lie outside where the pi electrons, the pi electrons are basically circulating above and below the carbon-carbon double bond, above and below that aromatic ring. They're outside that loop. They're in the region of space where that local field is reinforcing the applied field. Okay. So there might be a couple of theory questions, but by far it's applying the information to deduce structures that's going to be most important. How are you guys doing on, here's some spectral data, maybe some chemical information. Let's pull out a structure from this information, because that's really what you've got to be able to do. Want to work through some problems like that? Because I got plenty of them to pick from.
Sure.
Okay. Let's work through some problems. Let me switch to a different file. Where is that other? There it is. I've got plenty to choose from. These are from not your book, they're from a different textbook, but they're kind of instructive as to how we go about and solve these problems. So let me keep the spectral data kind of over on one screen, and I will switch to the document tab, so I can kind of show you how I confront these types of problems. There we go. Okay. So I'll put up a sheet of paper in just a moment. So we've got a molecule. It's got the formula C6H8O. Here's the proton NMR spectrum. This came from a textbook, so it's not giving really the multiplicity. But that one proton signal is a triplet. Okay. The two proton signal is also a triplet. This is a quartet, and then we've got a three proton singlet. So these are actually pretty straightforward to interpret just from the appearance of the signals. We've also got the C13 spectrum with depth information. Remember, the depth C13 NMR tells us how many protons are on each of the carbon atoms. So the way this is formatted, it's basically telling you how many hydrogens are directly attached to each of the carbons. So 6 carbons. What's the first thing we should do when we're confronted with a formula and we don't know the structure?
Hydrogen deficiency.
Index of hydrogen deficiency. I absolutely hate that term. Unsaturation number is a little bit more instructive because the number that comes out of the calculation tells us the number of unsaturation units. Every pi bond is an unsaturation unit. Every ring is an unsaturation unit. So, again, I put a handout up on Blackboard. It's the one that I basically utilize when I teach how to calculate that in Organic 1. So it's kind of my take on the calculation. What you've got to do is you've got to take the formula of the real molecule and convert it into what I like to call the equivalent hydrocarbon. How do we do that? Well, let me kind of outline the rules really quickly. To get the equivalent hydrocarbon, we ignore oxygen. If there's any oxygen present in the formula, just get rid of it. It doesn't affect the number of hydrogens. If we've got halogens, what we do is we replace each halogen with a hydrogen. So say we had something, C4H11Cl. We would take out that chlorine, replace it with a hydrogen, it would be C4H12. Okay. That's not even realistic. C5H11, that's better. That would be too many hydrogens. But you get the idea. Not relevant here. If we've got nitrogen, that's where it gets confusing. For each nitrogen, remove it, and also remove one hydrogen atom. It's almost like nitrogen carries along an extra hydrogen, so if you're taking the nitrogen out, take away a hydrogen atom for every nitrogen you're taking out. That's going to start to have importance later on in the semester when we start looking at some nitrogen-containing functional groups. So that's something that we'll have to remember, about 2/3 of the way through the semester. So what's the equivalent hydrocarbon formula for this oxygen-containing molecule? What do I got to write if I want to pretend this is a hydrocarbon? C6H8. I just ignore the oxygen. Well, all we've got to do to calculate our index of hydrogen deficiency, our saturation number, is we take, I'll just write the generic formula, 2n plus 2, where n is the number of carbons. We subtract the number of hydrogens in the equivalent hydrocarbon. And then that difference gets divided by 2. And that's the quick and dirty explanation of how you do in saturation number, index of hydrogen deficiency, more elaborate discussion in that handout. What's 2n plus 2 for this molecule? 6 carbons. 14. So we've got to take 14. There are 8 hydrogens present, actual molecule, equivalent hydrocarbon, same thing. That difference is divided by 2. 14 minus 8 is 6 over 2. Unsaturation number is 3. That means there are 3 pi bonds and or rings in the structure. Calculating the unsaturation number, the index of hydrogen deficiency, gives us valuable structural information. Because when we come up with a structure, there better be that number of pi bonds and or rings total, otherwise it's not a reasonable structure. Otherwise it can't possibly have the proper chemical formula. Okay. So we got to come up with 3 unsaturation units. Well, when you see heteroatoms, when you see elements that aren't carbon and hydrogen, trying to figure out what functional group might be present is useful. Now, we didn't talk about IR, but infrared spectroscopy gives us that information. So there is a question on part 2 of the test where I kind of give you a hint. You're going to be using NMR data to figure out structures, but I've given you a little extra hint by telling you IR data indicates, there's an alcohol, there's a carbonyl group, there's an alkene. Okay, we didn't talk about that, but you can get that functional group information from infrared spectroscopy. So don't flip out if you see the term IR. I'm really just using that to tell you what functional group needs to be present in your structure. I'm not even giving you the actual data, just a conclusion that can be reached from. There's oxygen. Okay. Well, when you see oxygen and you have at least one unsaturation unit, sometimes that's because you might have a carbonyl group. So let's think about whether this data is consistent with the presence of a carbonyl group. This is where the C13 spectrum has good utility. Because where do we typically expect to see carbonyl groups resonate in a carbon-13 NMR spectrum? Downfield. Where downfield? Where specifically? It's usually somewhere between 160 would be the low end up to around 220. There's a carbon that has 0 hydrogens according to the depth information with a C13 signal that's right, it's around 207 or so by that scale. I would say chances are there's a carbonyl group in this molecule. That's a piece of the puzzle. Okay? So we've accounted for one of the carbons. We've accounted for the oxygen if we assume that there's a carbonyl group left. Okay. Looking at the rest of the C13 spectrum, how many signals are there? There are 6 signals. There are 6 carbons. Does that mean that we have more than one of these carbons being equivalent to each other? Does that mean that there's symmetry? No. So all 6 of the carbons are giving a distinct signal. All 6 of them must therefore be in a somewhat different electronic environment. Okay, so that's an important piece of information. Well, now we've got to focus on the proton NMR. Up above 6, it's kind of around 6.3, 6.4-ish, there's a 1 proton triplet. Where do we typically see things coming into resonance, in that 4.5 to 6.5 neighborhood? What does our generic chemical shift information suggest that proton might be attached to? On what? On the well, you can't have a hydrogen directly bonded to the carbonyl carbon. How do I know that? Because in the signal for our C13, which is giving us depth information, there are 0 hydrogens bonded to that carbon. Go back and look at that general area. I don't want to pull that slide up yet again. But what things typically come into resonance between 4.5 and 6.5? You really are going to be well served if you know those general regions up here. Because that's going to only help you when it comes time to do this on Wednesday night. What things come into resonance between 4.5 and 6.5? Vinylic protons. Protons directly bonded to sp2 hybridized alkene carbons. So I probably have a carbon-carbon double bond where there is just one hydrogen attached to a double bond carbon. Why can I say there's just one? because the only signal in that vinylic region is that one, and it's produced by one proton. So what does that mean needs to be attached to the other 3 single bonds around that alkene double bond? They must be other carbons. What does the fact that that signal is split into a triplet suggest? That carbon that bears the 1 hydrogen must be neighboring a carbon that has 2 hydrogens. I say this all the time. Each bit of information is like a piece of the puzzle. Well, the fact that we have a chemical shift that is consistent with the presence of a vinylic proton, the fact that there's only 1 proton producing that signal, and the fact that that signal is a triplet, must mean that we've got a fragment that looks like this in the structure. Now I've accounted for 1, 2, 3, 4 carbons. This carbonyl carbon is unlikely to be this one because you usually wouldn't have a carbonyl carbon doubly bonded to another carbon. That's not a very common structure that we see. But we're starting to get pieces of the puzzle. That's the whole idea. Let's take a look at some more of this information. What do you think that 3-proton singlet is due to? A methyl group. A methyl group, how many carbon or how many hydrogens are on the carbon bonded to that methyl group? 0. How do I know 0? Because if it's a singlet, it must be neighboring 0 hydrogens. So that's a piece of the puzzle. That's also our 1, 2, 3, 4, 5th carbon. Okay. Well, and that would have to be the only methyl carbon, and the depth information is giving us information. The number of hydrogens, so that's valuable information. The depth is telling us there are 2 CH2 groups. Well, that's also suggested by what we see with these signals. 2-proton signals are usually caused by CH2 groups. What does this 2-proton triplet suggest? If it's a 2-proton triplet, what's that CH2 group next to? It must be next to probably just another CH2 group. Well, maybe I have something that looks like this. But then this carbon is adjacent to 2 hydrogens over here and 1 over there. What's this signal look like? Kind of looks like a quartet. Total of 3. If those coupling constants happen to be the same, then even though these 2 protons aren't equivalent to this one, it looks like we might have, 4 lines in this signal. So we've got 1, 2, 3, 4, 5, 6. We just need to put this all together somehow. Well, maybe my CH3, I think I heard somebody say this, you've got to have a methyl group on one of those vinylic bonds. Where does that leave the carbonyl group? Now I got a piece that has 1, 2, 3, 4, 5. Where's this got to go? Put it there. There's an unsatisfied bond. That carbon only has 3 bonds as it's drawn. Huh. Let's see. I have used up 1, 2, 3, 4, 5, 6 carbons. 2, 4, 5, 8 hydrogens. 1 oxygen. This is looking like it's got all the pieces, but there's an unsatisfied bond here. There's an unsatisfied bond there. What do you think we got to do to those unsatisfied bonds? Bond those carbons to each other. Closing up a ring gives us our third unsaturation. That's a more elegant way of drawing that molecule when I close up that ring. Does this look consistent with the data? Well, it's certainly got a carbonyl group, it's got an alkene pi bond, it's got a ring. 1, 2, 3 unsaturation units, it checks out in that respect. It's got the right formula. This methyl group, it's next door to an alkene double bond. Essentially, that methyl group